Hi, today let's have a look on several electromechanical devices. So this thing seems to be a switch. I don't know, there is something written here, but very difficult to see. It is written differential pressure switch, okay. Obviously there is a membrane in the middle and one pressure here, the second pressure on the other side, and there is a switch on that protuberant cylinder here. Okay, look at that. There is an O-ring. There was something in the middle which is somewhere on the floor. This is a kind of Kapton film. Okay, and the switch is here. I don't know why this thing is so big. Actually, this thing is soldered. Okay, I will try to cut here in order to see what is inside. Okay, so this is just a micro switch. So of course an important thing on that device is transmission here. So I think that this thing is adjusted, and after that the cover is soldered. So this is the airspeed switch. It is set at 220 knots. And the switch is activated by the expansion of the aneroid capsule here. So we can see that there is a small PCB with 2 transistors on that thing and a few passive parts, one diode also, 2 relay. This is maybe used to activate the relay. The commutation is done by the contact between the aneroid capsule to that thing here. Okay, so there is just a screw. I don't know the purpose of these transistors. The switch contact corresponds to the blue wire here. It is connected to one capacitor. There is maybe a filtering with a capacitor here. So this permits to drive the relay, which is here. The displacement of the membrane here is proportional to the difference between the internal pressure of the capsule, which is the pitot pressure, and the internal pressure, which is the static pressure. So this thing is obviously sealed. Okay, so let's continue with this accelerometer. Something was written here on this sticker, but it is more or less erased. This thing is full of oil. I have cut the top here. Oh, look at that. Okay, and these parts are military parts. You cannot read the reference of this IC. Okay, it's a LT1001. It should be an op-amp. And this one here is an LT1014, a quad op-amp. Okay, I think I will cut the wires. It will be easier. You can see that there are also other boards. Okay, so there is one accelerometer here, another one, and the third one is here. Okay, so you can see that there is a mass here. So it seems that there is a very tiny strain gauge here. Okay, so this one, for example, works on that direction. So when an acceleration is present, there is a displacement of this mass here. So this is the bridge configuration. You can see 4 wires. The voltage created is very small. So this is why there are several precision op-amps on that system. And it seems that there is also a resistor here for calibration, probably. 33 ohms or something like that here. So this is obviously a differential amplifier. You can see that some resistors are selected. So I think that there are 2 stages. One stage using this LT1001 and another stage using one of this quad op-amp here. So this is interesting. This is a nice device. This is a schematic diagram of one channel. There is a first stage which permits amplification of the signal of the bridge here. And there is a second stage which is a second order low pass filter. The first amplifier uses an LT1001. This is this op-amp here. And the filter uses one part of the LT1014, which is this part here. So we can see that the output of the bridge is connected directly to the input of the op-amp. Actually, the output of the bridge is short-circuited by the op-amp here. The gain is defined actually by the ratio between the feedback resistor, which is 74 kilo ohms, and the equivalent internal resistance of the bridge. I have measured a value of 1 kilo ohm exactly for one resistor. So the source resistor is 500 ohms. Therefore, the gain of the amplifier is approximately 150. The bridge is supplied with a voltage of approximately 12 volts. Something interesting is this resistor here. In order to understand the purpose of this resistor, some calculations are required. When there is a displacement of the mass, there is a change of each resistor of the bridge. For example, there is an increase of these 2 resistors and a decrease of the 2 other resistors here. It is possible to simplify this circuit. On the left side, these 2 resistors can be modelized by a voltage V0 plus delta V with the source resistor equals to R0, for example. On the left side, there is a voltage of V0 prime, which is a little bit higher than this one because of this resistor, and this time minus delta V. There is a variation of plus delta V on the left and minus delta V on the right, for example, but it can be on the other direction, depending on the direction of the displacement of the mass. This is the simplified schematic. The left side of the bridge is modelized by a voltage of V0, which is actually half the power supply voltage of the bridge, plus delta V, and we have on the right voltage of V0 prime, which is a little bit higher than this one, because of the resistor which is added, minus delta V, and there is also a source resistor, R0 prime, which is a little bit higher than this one. I have done the calculations. It is not very complicated, just a basic electronics calculations. As you can see, the output voltage, Vs, depends on the voltage delta V, of course, which is proportional to the displacement of the mass and also to the power supply of the bridge. This is the gain of the amplifier. And we can see that there is another value which depends on the power supply of the bridge. If you consider that the additional resistor is not present, you have this value V0 R0, so you have something which depends on the power supply of the bridge. Actually, so this is a common mode factor. You can see that if the additional resistor is present, it is therefore possible to choose a specific value of this resistor in order to null this term here. In that case, you have a rejection of the common mode. Okay, I have connected this device to a power supply of 20 volts. You can see that this thing works. The range of this channel is plus or minus 1G. So this is this first channel, left and right. So we can see that in that direction there is a voltage of 5 volts approximately, 2.5 and 0 volt on that direction. So this is effectively plus or minus 1G. Okay, you can see resonant frequency. The period is approximately 66 milliseconds, so this corresponds to a frequency of 15 Hz. So this is the sequencer for something, I don't remember. Look at that, this is effectively a sequencer. I succeeded to remove 2 screws. The 2 others are very difficult. Okay, so I drilled 1 screw here. It should be possible to rotate the cover. Yes. So I think that this is just a junction box. And this thing is seriously constructed. Let's see the last thing. This thing is a wing sweep angle transmitter, that code 8716. This was manufactured by Doughty Electrics Limited. There is a shaft here. This is the input of the transmitter, obviously, because there is nothing else. And on that side, there are 3 connectors, 1 large and 2 others with less number of pins. Okay. Oh, there is nothing special, just 2 potentiometers. There is a large demultiplication. Okay, we can have a better view of the mechanical stuff. Okay, look at these ball bearings. Oh, this is a serious construction. You can have a look on the potentiometers. This is the Penny and Giles Limited Blackwood. There is a reference. This seems to be a particular thing. And this one have 5 gangs. And this one too. These potentiometers should cost a fortune, I think. There is a little pleb. The connectors are made by Sorio. This is a French company. You can see the reference 3526 00G 146 14B. That's all for these electromechanical devices. Thank you for watching and see you next time. Bye bye.